Here's our initial value problem. dy dt equals 70 minus y of 0 equals y naught. This differential equation does have applications. The application I have in mind is to cooling. Like if you're in a room that's 70 degrees Fahrenheit, you could also say heating or warming. If you've got something like hot chocolate or coffee or something that's hotter than 70 degrees, and you're letting it sit in a room and cool down, if you let y be the temperature of the coffee as a function of time, its rate of change of that temperature with respect to time could equal 70 minus its temperature, y representing the temperature, meaning if y starts out at 120 degrees Fahrenheit, 70 minus 120 would be negative 50. At that moment in time, that would be saying the rate of change of the temperature with respect to time would be negative 50 degrees per minute. That seems like a very rapid cooling. Maybe degrees per hour. Maybe time is in hours. As it cools like down to 100, 70 minus 100 is negative 30. The rate of change is still negative. The coffee is still cooling down, but it's slower. The graph of the temperature versus time is going to be decreasing, but concave up, it would turn out. Anyway, let's go ahead and solve this with separation of variables. We want to get all the y's on one side and all the t's on the other side. Well, there's only one place where you see a t in the dt. You pretend that's a fraction, and you pretend you're multiplying both sides by dt. We won't have enough time to justify that today, but we will next Wednesday. And then divide both sides by 70 minus y, and what you get is dy over 70 minus y equals dt. And you're used to looking at this kind of thing and saying, I guess I better integrate both sides now, and yes, that's a good idea. But while the right-hand side is easy to integrate, the left-hand side is a little tricky. Yes, you get a logarithm, but you also get a minus sign because of the minus sign right there. If you're unsure, you can always check that by differentiation. You also could do a substitution if you want. U equals 70 minus y, and then du would be negative dy. So negative natural log, do you need absolute value signs? Well, okay, I always put them in there to start with. But then we, in this class, at least always end up getting rid of them anyway. So it's not a real big deal. I won't mark it wrong if you don't put absolute value signs there. Plus c, but I could subtract the c on the left side from both sides and put it on the right. So I might as well just only put in a constant of integration on the right. Should I call it c or c1? It doesn't really matter much. I'll call it c1 just for a little bit of clarity. That'll have different constants, but they're all arbitrary anyway, so it doesn't really matter much. I want to solve for y. It is important to have that negative sign there, and now multiply both sides by -1 and put that negative sign in front of the t as a negative t. Minus c1, or maybe how about plus c2, where c2 is negative c1. And again, you can be sloppy here. If you make these both c's, I'm not going to count it against you. Ultimately, we just want to make sure we get the right answer in the end, and so it's not a real big deal if we're a little sloppy here, as long as you're not too sloppy and it causes you to get the wrong answer. Exponentiate to get rid of the logarithm. Get the absolute value of 70 minus y equals this. But by a property of exponents, that's the same as this. And hey, I suppose maybe we should call this C3. Or just a plain old C if you want. Being sloppy. And okay, now we'll go ahead and get rid of the absolute value signs. And we sort of pseudo justify that by saying C3 becomes just, say, a plain C. So C3 is like, well, C is plus or minus C3 or something like that, or C3 is the absolute value of C. Hand-wavy math, we're not worried about getting things real super precise. We're after the right answer in the end. Solve for y, we're almost there. I'll do two steps at once, add y to both sides and subtract c e to the negative t from both sides, although, okay, maybe I should call this a C4 and do it this way, where now c is negative C4, okay? That's a general solution. A general solution of the differential equation. DE for differential equation, or you could call it diff-EQ for short, or ODE for ordinary differential equation. It represents infinitely many solutions. C is arbitrary. The differential equation has infinitely many solutions. But if I have a specific initial condition, like a 5 there, or a why not, where I'm saying why not is something specific, a constant, then I only get one unique solution of the initial value problem. Very important comments here that I'm making. There are infinitely many solutions of the differential equation represented by your general solution. C is arbitrary. But when I have a specific initial condition, and I'm pretending why not is a specific number, it's in my head, I'm saying to myself, it's a specific number, then C is going to be something specific in terms of why not, and that's one solution. So you find C in terms of why not by replacing T with 0. Here, C does not equal why not itself, like it did last time. C, if you write the general solution in that form, equals why not minus 70. So the solution of the unique solution of the initial value problem is y equals 70 plus, looking here and replacing C with 7. Oh, sorry. Replacing C with y naught minus 70 using parentheses times e to the negative t. That's my unique solution of the initial value problem. That's the answer. Can we graph the solution? Not unless we know what y naught is. Though if it's cooling coffee, y naught would be bigger than 70, right? Like 120 or something. 120 minus 70 is 50. It'd be 70 plus 50 e to the negative t. Let's like taking an exponential decay and translating it upwards by 70 units. The graph would have a horizontal asymptote at 70. The graph is going to look something like that. That's what your cooling coffee looks like. That's the temperature versus time. Y naught is really the y-intercept. Maybe it's 120. This model actually works for warming coffee too. If you've got cold coffee, Y naught is less than 70. Then that's a negative number in front of the e to the negative t. Like negative 50 e to the negative t or whatever. That's like taking an exponential decay, first reflecting it across the horizontal axis, so it's an increasing function actually, and then translating it up. It would look like that for warming coffee if it starts out cold. This is an oversimplification. If you got your coffee sitting in a mug on the table, it's not going to warm or cool uniformly, right? Because there's spatial effects. The temperature in the middle of the liquid is going to be less affected by the ambient room temperature than the fluid near the edge or near the top of the fluid level. The mug also insulates to some degree. There are spatial effects that technically need to be taken into account to be super accurate. That actually is going to involve a partial differential equation instead of an ordinary differential equation. Partial meaning partial derivatives involve more than one independent variable, not just time, but also spatial variables. So this is just an oversimplification. You can make it as good as possible by stirring your coffee periodically. Right, that'll mix things up and the spatial effects won't be as prominent. This model is actually called Newton's law of cooling and or heating. It's got that as its name. One more comment. In this class, not in our textbook, but in lectures and in class here, the video lectures and in class here, I'm often going to give this function a name. I'm going to call it, well, a Greek letter, phi or phi if you prefer. Phi of t is going to be the name of the solution. Our textbook does not use this notation, but other differential equations textbooks sometimes do. And I'm even going to do a little bit more. I'm going to use the initial condition, y naught, as a subscript. Phi sub y naught of t. Subscripts within subscripts here. It's a function of t, and y naught is the initial condition. This is going to be very important for us in a month or two, especially in October. It's going to be a big, big deal. So we want to do this sometimes. I will, in fact, try to do it consistently to get you used to it. In the differential equations textbook, this right-hand side of the differential equation is often given a function name as well. That's typically called f of y. That's the right-hand side of the differential equation, f of y. This is the solution, phi of t, or phi of t. Phi, phi, don't call it pho or phone, though. Phi or phi. Mathematicians tend to say phi. Physicists and engineers tend to say phi. I don't know why, tradition. I asked a Greek professor, is it phi or phi? And they said, either one's okay. You know, fraternities and sororities say phi, whatever. I like phi because I'm a mathematician.